So good morning, everybody here. We shall not wait for anybody. Or okay, we'll wait for a couple of minutes and then we'll start. So let's start. My name is Anna Semenkova. I work here in radiochemistry department, and my work is devoted to characterization of different materials that are often used as engineering barriers or radioactive waste repositories. And today we will talk about engineering safety barriers providing the isolation of nuclear facilities. Something's okay. So nowadays, the isolation of radioactive waste from the biosphere is an important task of nuclear industry all over the world. You can see here on the map that so many nuclear industry facilities like nuclear power plants or radioactive waste storages are located all around the world. So this problem is relevant for many countries. Actually, the most of countries have very similar approaches for creation of different types of repositories for radioactive waste. And we will talk about different types of repositories, about requirements for the engineering safety barriers. We will talk about several examples for repositories and those characteristics which are necessary to determine to select the correct materials for the barrier material. I'm sure you've heard in the previous lectures about different types of radioactive waste, from very low, very short-lived radionuclides up to high-level wastes. So when they increase their period of the decay time and when the radioactivity increases, their wastes become more dangerous and more strong requirements are for their barrier systems that should be surrounded this waste. There are several recommendations for the radioactive waste repositories depending on their level of activity. When we talk about very low levels, they should be disposed in they can be disposed in the ground level or a little bit deeper in the ground. With increasing the radioactivity and the decay, the preferred barrier systems that can be located at the top on the ground or deeper in the ground. And for intermediate and low and high level wastes, high activity wastes, storages should be located deep in the earth. For intermediate level waste, about 10 or 100 meters, 100 meters. For deep repository, it is about 500 meters. And of course, then the more dangerous radionuclides are in the repository, then more strict rules for the barrier materials, then most complicated the barrier system should be. So when we talk, the main idea of the barrier system is to prevent the is to protect the environment from radionuclides that are in the repository. So as we all know, wastes are in the solid form. They're packaged in the repository as solid form. So they can go outside only as liquids. So do you have an idea where can liquid come from? How water can intrude into the repository? Yes, and more usual maybe ideas, something more usual in nature, what happens? Okay, so cracks, of course, usually we talk about even rains. So if rain comes to the top of, here is the repository, disposal of the radioactive waste, rains, they get inside the repository and they can wash radionuclides outside the environment. If we have any cracks or if we have groundwater allocated closer to the repository, there is another danger. So of course it is, and it should be taken into account when we create the safety barriers and when we create our disposal or repository. Because when the radionuclides are washed away, they can get into the river system, oceans, and so on, and it can be very dangerous for humanity and for the environment. And the radionuclides can migrate very far, so that we should prevent it. So I'll skip this slide. Actually, there are several ways how can radionuclides get away. The different mechanisms that provide radionuclides migration. First of all, the filtration. If you have a big water flow, radionuclides will go with it. So the main idea of the protective barrier is to avoid the filtration. So that the migration will be possible just due to the diffusion process. It is very, very low, and sometimes sorption, but often it is included into diffusion. I will talk later about it. So the main idea is to protect and to avoid any water flow, any strict water flow. So for all engineering barriers, there is one principle, the multi-barrier principle. It's like if you go outside in a cold weather, you will have several types of clothes. You will have a wool sweater, or you have a jacket that will protect you from rain, snow, or wind, and so on. And the same is for radioactive wastes. They have different layers. Depending on the type of the repository, it will be 1 or 2 layers or maybe more. So all barriers should work in different ways. They should contribute to a long and safety stability for several functions, from physical containment or chemical containment for the repository, engineering, and so on. And of course, there should be geological isolation to prevent any leakages or leakages of intrusion of water inside the system or outside with the radionuclides. So here are several examples of multi-barrier systems that are commonly known for radioactive waste. Here you can see that first of all, it is then examples for the high-level waste, but the same principle, it works for all other wastes. I'm sure the presentation will be available after the lecture, so you can just take it for pictures later. So the first of all, we solidify all liquids, all waste, and we put them in a kind of matrix, cementitious or glaciers, or anyway, different types, depending on the type of waste. After that, we put it in a metal canister. Here is an example of Sweden, they work with copper canisters. That the canister should work for hundreds of thousands years and to prevent any leakages. After that, there may be destroyed due to radiolysis or any other problems. And so the next protection level is the creation of big barrier. For example, here is the thickness of metal layer of canister, about 5 millimeters or something like it. maybe up to some centimeter. And here we talk about 50 centimeters or even meter, half a meter or meter depth. So usually here we use nature materials such like clay, soil, sometimes sand, but it's not very good. I'll talk later about it. So, and after all, everything it is located in the big host rock. It may be clays or rocks, granites, or soils or something like it. It depends. So, and all the system with container and soil or kind of buffer material, everything here is called an engineering barrier. So sometimes, and here you can see that how it can be located for another type of waste. It is everything is covered here. Here you have a tunnel. We put the canisters and some buffer on the top, and everything is deep in the host rock. I think we will talk more today. We will talk more about buffer materials that are used for creation of engineering barriers. IAA gives different recommendations for using of clays. Clays are very good for this suppose because they are very widespread. Sorry? Yes, exactly. They have high sorption properties, they have low diffusion properties, and so on. So IAEA recommends to use for creation of low level or very low level waste disposals, some kind of trenches that bottom of them is filled with the special geomembranes, and if we will need to use such disposals for longer periods of time, more than 100 years, it is also possible to use special bentonite barrier. Sometimes there are new materials that are constructed especially for this supposes for it, and it has a special covering geotextile that provides that isolates everything from the water intrusion. Then you have a special bentonite that has good sorption properties and special supporting geotextile downstairs. So we can put such material on your trenches and put after that radioactive waste and fulfill it with sometimes even with the same material, or you can have some layer of the soil or clay on the top, and sometimes it is even possible to create roof or some building on the top for the low level radioactive waste. For intermediate level waste and sometimes for low level waste, it is necessary to use an underlying layer of bentonite. Sometimes it is possible to use it mixed with sand or local soils. And of course, it is when we put for intermediate level waste, when we have containers containing radioactive waste, we should fulfill the space between them with the bentonite. It is the recommendation of IAEA. So here is an example for how does it look like. So here is a tunnel where you borehole where we put intermediate level waste. Here is the buffer material, or here is the buffer material, and we make some kind of walls around, like from cement or something like it. Here is the packages with the waste, and everything should be surrounded with buffer material bentonites. And tunnels should be also backfilled with good sorbing mixtures. Actually, IAEA doesn't give strict recommendation due to the low-level waste and so on. But there are a lot of works and very strict requirements for the high-level waste repositories. So we have the same principles for all repositories, so we can be guided by results of work obtained for deep repositories, and we can use them when we talk and when we create repositories or disposals for low-level waste, very low-level waste, and so on. We will briefly talk about containers for radioactive waste, or maybe you've talked about it previously. Okay, just briefly. So there are several questions that should be taken into account when we use containers. So we should ask ourselves, what about activity of radioactive waste, total activity, activity of alpha, beta, emitting radionuclides, and so on. So we should note that there can be surface contamination of radioactive waste packages. And of course, in case when we use containers for storage or transporting, we should take into consideration the mass size parameters, the weight, the volume, and so on. Usually metal containers or special reinforced concrete containers are used. Here's an example of one of the famous or widespread containers that used in Russia. This is a non-returnable protective container. So it can contains barrels with solidified waste, and it can contain about 1.5 cubic meter and a half of solidified intermediate level waste. So such canister is located into the disposal, and it is not returnable. There are some other types of containers that are designed for another ideas. Here is the example of metal container that is created for collection of intermediate and storage of intermediate waste for transporting. And this type of container is returnable. So if you don't need it anymore, you can return it back. And here is this big container that is designed for the disposal of solid radioactive waste. So here are the general requirements for creation of engineering barriers. Sometimes in some works, when we talk about engineering barriers, we mean that we talk about buffer materials that fulfills the area around containers and so on. So what should do the engineering barrier? Of course, it should delimit contact of radioactive waste with packages with radioactive waste with environmental and with environmental water. That is most important. It should prevent the destruction of radioactive waste packages under natural and technical impacts. It means that sometimes earthquakes or something can impact on the stability of your packages with radioactive waste. So the buffer material should avoid it. And of course, buffer material and all engineering barriers, they should limit distribution of radionuclides into surrounding. And all these barriers, they should work for the time of decay of radionuclides inside the repository, or it is the time of operation of this disposal place. So other requirements for the barrier materials. If we have any cracks or leakages of radionuclides outside the repository, it will be dangerous, and it will provide their distribution to the environment. So first of all, we should stop or minimize leakages of containment beyond the barrier. To provide it, we should choose materials with low filtration and low diffusion properties, but with high sorption properties, and we should choose those materials which also have very low disruption of radionuclides from themselves. Next, it is important to note that some radionuclides can migrate very far and very fast when they are sorbed on colloid fractions, on very small particles of barrier of soils or something like it. So we should choose our materials so that they will have low or have no ability to form colloids, or make maybe some and they should not contain some organic substances that can increase radionuclides migration. So this it means, and the next is that barrier should be should work for all the entire period of operation, so it should be very stable over time. And in this case, natural materials that are they are good. So as you know that maybe natural clays, they can be formed million years ago, so and they will have their properties and thousands and hundreds of thousands years more. So as I already mentioned, so the barrier materials should be resistant for tectonic movements and so on, and it means that it should be very plastic. It should have a good plasticity. Of course, all components of engineering barriers, they should be safe for environmentals. They should be safe in case of fire or explosion, and they should not be toxic. And of course, the last, but it's not the least, that materials should have acceptable cost, and they should be available on the place where you want to dispose your radioactive waste. Usually, in case when we talk about buffer material, all around the world, natural materials are chosen like soil, sand, or clay, or their mixtures. But due to their unique properties, usually, and when we talk about high-level waste repositories, bentonite clays, they are chosen as the preferable component. So I want to tell you why bentonite clays, they're so good and preferable in all around the world when we talk about high-level waste repositories, and so it is very good suitable for repositories of intermediate or low-level waste. So first of all, they have low water permeability and ability of self-healing. Here you can see the picture, but that have a small block of bentonite, and when we put it into the water, you can see that it increases in size. So if you have cracks inside your barrier and the water comes into, bentonite will heal these cracks. It is very good in case of long-term stability of barrier. Of course, the bentonite have long-term stability because of its natural material, very stable and so on. And they have high sorption properties, and in many cases, they demonstrate very low desorption of radionuclides. And they have low diffusion comparing for another natural materials. So such unique properties of bentonite clays, they are related to the presence of special mineral montmorillonite. Here's its structure. Bentonite clays consist from montmorillonite for about 50 or more %. And of course, there are some other admixtures. Montmorillonite is a mineral that consists from sheets of tetrahedrons and octahedrons of aluminum and silicium. And there is a special interlayer space where can be sorbed water or any cations. And due to isomorphic substitutions inside the structure of these sheets, there is some negative charge inside outside the structure here or here. And to compensate this negative charge, cations can be sorbed. So this is one of the reasons why even when bentonites are preferable for use as a component of engineering barriers. So, here's several examples of disposals of projects for disposals of high-level waste. And far as I know, in the world there is no one repository that is already operating. So here is an example for Asper hard rock laboratory. They were scientists for more than 20 years. They checked everything that happens with the barrier materials, with the canisters, with the wastes, and so on, under real geological and environmental conditions. So they made several boreholes, about 500 meters depth, and they made several. I think I'm talking. And the second is Grimsel test site in Switzerland. When in both of the laboratories, scientists performed very good work. They real long work. And they made boreholes. They performed different experiments. They were controlling how changes the properties of buffer materials for long periods of time, 10 and 20 years, when local water intrudes, when they have a heating like from radioactive waste canisters and so on. And after that, they took the material outside and they checked how did it change and what happened and how will it be suitable for longer use. Here's an example of, here's a clay, here's a rock formation, bentonite clays and canister. And in all experiments, they used, in some experiments, were used special heating elements to control how does this buffer material changes. And outside, sometimes there were some leakages and water intrusions and so on. And here is an example of experiments that were performed in such experiments. They controlled formation of colloids, performed light scale modeling and long-term cement studies and so on. Every layer of engineering barrier was checked in case of long-term stability. And we have a lot of works devoted to the question of application of bentonites as engineering clay barriers. And what is I want to notice that it is important to take into consideration the conditions of a particular site, because due to their differences, sometimes it is possible to select a little bit different types of barriers that will work better. So here's an example for long-lived low-level wastes. They can be located on the top of the ground, upper than ground level, and inside the ground when groundwater is surrounded. And usually when we talk about low-level radioactive waste disposals, it is located not deep in the earth. It's about 10 meters or less, and it has several layers of protection. It is covered with soil, with grass and so on. It has special rooms with containers, canisters and so on. It has a drainage system to avoid leakages of water inside the barrier. And everything is surrounded with the buffer material. So the same as for high level waste, but located closer to the earth. And here's an example of disposal of repository for short-lived, low and intermediate level radioactive waste that is created in Lithuania. So they made some walls and roof and located it on the top of the earth and have some geomembranes and barriers downstairs. Here's an example of management of radioactive waste. This is in Sweden and in Japan. So you can see here that there's a layer of soil, there's ground level. They made bottom for about more than 1 meter to avoid any leakages in the environmental. Then the canisters and barrels were located, and they have put it on the top the mixture of bentonite and stones for about half a meter, and everything on the top was covered with mixture of gravel and stone. And for example, in Japan, when they had to dispose their soils after Fukushima, they decided to make a repository on the principle of trenches. So to prevent radionuclides from penetrating into groundwaters, they covered it with buffer material. You can see it here. After that, they put their waste and covered everything with a buffer material that contains soil, and this thickness is about 1 meter. So you can see that the size of the isolating material, it depends, and from the it can be different for different types of waste and for different types of repositories. And why is it important to take into consideration the barrier system? Here's the example of the first radioactive waste redisposal. In Hungary, there was a Solimar site that was operating in 1950s up to 1980, and it was located very close to Budapest, and there were no any systematic requirements for the disposal of radioactive waste. There was not any characterization of waste that were located there. So after 1980, it was seen that this repository is not suitable for the canister, and they found radionuclides rather far away from the disposal site. So after that, they decided to make a new repository and they created it, and they moved all the waste that were located in Solimar site to this site, and they made the different types of disposal, like concrete trenches or shallow wells. And here you can see it. And nowadays they control and monitor everything, and they have a rather good situation. And here is an example. And they also created one more disposal point in Batapini that is located near nuclear power point PAX, and there disposed containers mostly from the nuclear power plant. And in United Kingdom, there are many places where radioactive waste are disposed, and the most common known is Drigg and Sellafield. Yes, exactly. But I will want to show you, tell you a story about Drigg site. So it was an operation in 60s, and they made a series of trenches, rather good, for about 8 meters deep. They put wastes in barrels, sometimes even without barrels, and they fulfilled everything with soil. But about 30 years later, they found that there occurrence of leakages outside such repository. So they decided to build a new battery system to prevent radionuclides intrusion. And they made special concrete hoopers. They put all radioactive waste in metal containers. They fulfilled the space between containers with cement, and have 12 layers of coating on the top. But about 15-20 years after the separation, they understood that there is water inside the system, and some metal canisters, they have corrosion. And corrosion, it means that canister will not work for a long time more. So they even found that there were leakages into the sea that was located rather close to this object. So it means that cement barriers, they're not very good. They're not very stable in time. It costs less than 20 years, and they don't work more. So that's why I've been talking a lot about why natural materials are preferable. So in Switzerland, they were thinking a lot about creation of deep geological repository for high-level wastes. Here's an example. They wanted to put it in the host rock that is very stable, and for intermediate level waste, they wanted to store them around high level, maybe a little bit higher, not in so deep. And they have the system of protection, as I've already mentioned. They have canisters, then they're surrounded with the backfill material. We don't have a lot of time, so I will skip some. So on the same ideas in all around the world, Belgium, Japan, USA, and so on, several types of barrier layers that will protect environment from radionuclides. So I wanted to talk to you a little bit about conservation of special radioactive waste, but I don't think we have enough time. Here's an example for where we can use modern techniques to create the additional safety barriers around existing facilities. Here is two types of technologies: wall and soil technology. When we make big trenches very deep around like basins or something like it, and we take out the soil and we fulfill it with any preferable barrier material, and we make just like a wall around this object. It is even possible to make it downstairs the object. It's more difficult, but it is possible. And the other technique is jet grounding technology. When we make a borehole and under pressure, we put special mixture of good sorbing materials, and we can make these boreholes very deep, up about 30, maybe even 50 meters deep. And when we make them in shaft pattern, we can make very good, again, we can make something like a wall, so that will surround the dangerous facility. So here is an example. I like this picture very much. The modeling of the effectiveness of clay solid barriers for waste facilities. This barrier was made with the jet grounding technology. And here you can see that here's the spreading of uranium, if without barrier in 400 years and in 1000 years. Everything, all uranium goes outside and into the water, into the river system. If we have, we will make 1 meter depth columns, these columns, 1 meter depth, you can see that leakages are much less. But it we'll make 3 meter vertical barrier, so up to the water level, groundwater level. I mean, you will see that there's very stable and ready for 1,000 years, and radionuclides will not go away. So there are different characteristics of barrier materials that are important for creation of barriers, and that should be always taken into account when we choose them. We should also take into account the influence of site-specific conditions that can change sorption diffusion characteristics very much. Of course, nuclide composition should be taken into consideration, because some materials can sorb different radionuclides by different ways with a different effectiveness. We should take into consideration the solution composition. For example, here's the composition of two waters that were used in Grimsel test site and in Asper laboratory, and you can see that the concentration of components of the differ much, and such difference cause the differences in sorption and diffusion properties of materials. Of course, it is important to take into account aerobic or anaerobic conditions, because, for example, some radionuclides, uranium, they can precipitate when carbonate, when their carbonates from air are available. Temperature also significantly makes a significant impact. And of course, the formation of colloids. Different materials have a different ability to make colloids. So here I wanted to show you, to talk a little bit more about which characteristics should be considered to choose the better material. Here, for sorption, there are possible several different types of sorption sites. For example, here's the exchangeable cations with water in the interlayer, and special sites on the edges that are available for sorption by another mechanisms. Okay. On the slide, I wanted to show you the functions of bentonite, or why bentonite clays are often used for isolation as buffer material. So sorption, good diffusion characteristics, they are very have good plasticities, and they're stable during operation times, and very important sealing of open cracks in large pores in rocks, where due to their ability to swell. So how does it look swelling? You have small particles of clays, and when water infuses, they take water in the interlayer space. You remember here. So here is interlayer space, and water can go inside. And these particles become bigger and bigger, and they swell. So why is it important? Because when these particles swell, there are no place between them for water to water flow, and the filtration properties of montmorillonite is higher than comparing to other clay materials, natural clay materials. And it is due to their the presence of interlayer space in this structure. So it is also one of the important characteristics is diffusion properties. So here we compared the different types of clays, montmorillonite and kaolinite. Kaolinite doesn't have any interlayer space, but in some case, sometimes it was used for creation of safety barriers. So you can see that diffusion coefficient is rather high for tritium and chlorium, but when we increase the montmorillonite content, the diffusion coefficient goes down. It means then lower diffusion, then better. So diffusion becomes slower when we increase content of montmorillonite in the sample. Also, when we increase dry density of the sample, diffusion also increases. That's why sometimes it is necessary to use not just powder of clays or bentonites. It is better to use уплотненные dry and pressed blocks or pellets made from this material. So, and also when montmorillonite fraction increases, the diffusion coefficients for anions decrease significantly. It is very important because on other materials, we don't see this effect. Here is an example, how do we make our diffusion experiments. And you can see that for different radionuclides, diffusion coefficients and total mass flow is differs much. Here is tritium that is not sorbing at all, and you can see that total mass flow is rather big, and uranium sorbs much better. But it is also important to take into consideration that cations, they diffuse and they sorb at the same time on this material. So here's an example of the influence of montmorillonite content on diffusion. So when we have mixture without montmorillonites, diffusion is high. When we add montmorillonite, we have it's rather pure montmorillonite. The diffusion is very low, and it is significant for sorbing for ions. So Here an example of different processes that that can be observed in the system when we talk about sorption. So it is formation of aqueous complexes. It can be migration with colloids. It can be co-precipitation or precipitation of pure phases and so on. And all these processes should be taken into consideration when we determine the stability of this barrier material. For how long time we can protect our environmental from these radionuclides inside the repository. So everything what can happen with radionuclides when they are in environmental. It is also interesting that radionuclides can spread into pore space of rocks or other materials, and it can retain there and then can be washed away again. So here are factors that affect. I want to show you this picture because here is an example of uranium that depending on their pH of solution, you can see different forms. Here you can see that sometimes here it is even possible to find precipitate of uranium that will not migrate. But here, if we will talk about pH about 2 to 8, it is possible to migrate. And depending on the concentration of radionuclides, of the temperature, of the content of air or CO2 from air, this picture can change much. And here's an example that even nature water, it differs from point to point. And if you want to make a repository, you should take into account the conditions for direct repository. Here's the influence of temperature on sorption. So you can see that when we increase temperature, we increase sorption properties. And they're actually, just have a couple of minutes, so I will briefly talk about sorption on aluminum silicates and bentonite clays directly. So here's an example for europium, but why I use them because this radionuclide, or this cation, can sorb by two main ways as other radionuclides. It is ion exchange and complexation. Ion exchange happens on the planar sides or in interlayer space, and complexation it is on edge sides with functional groups. And this type of interaction is very stable. Is usually more stable than ion exchange. So it is. There are several factors they can affect on sorption. For example, it is surface area. When we increase surface area, we have more places where cations or radionuclides can interact. So when we increase the surface area, the sorption properties increase. Here we show the concentration of sorption sites for the material. And you can see that when we increase sorption, when we increase the concentration of radionuclides, when we have a low concentration, everything is sorbed about everything, about 95–100%. But when we increase concentration of radionuclide, you can see that for some materials, here's an example of kaolinite, the sorption is lower, and more than half of radionuclides can be washed away. For example, bentonite has better sorption properties, and even for high europium concentrations, they demonstrate sorption about 100%. So again, bentonite is much better than sometimes even local soils. It is also important to take into consideration the presence of different types of impurities. For example, when we talk about corrosion of canisters, we have different compounds of goethite and so on. And you can see that here's an example of clay that contains 3% of goethite. And clays that purified from it, and some natural clay, bentonite clays, and the content of monoperlonite in clays is very similar, but there's much higher sorption on the sample that contains iron phases. And it is also interesting that sorption on different types of clays can differ much. Here's this example for cesium that is widespread in nature after Chernobyl accident or Fukushima, and it is also contains in radioactive waste. And you can see that the sorption kaolinite is very low and much lower comparing to the bentonite. And if we will compare bentonite and mixture that contains 35% of kaolinite and pure kaolinite, we can see that decrease of bentonite content, the decrease of sorption of cesium with the decrease of content of montmorillonite in the sample. And also that I wanted to take out from our lecture that even bentonites from different repositories, they have a little bit different properties, sorption properties, and maybe diffusion. We're still looking on it. You can see that at low cesium concentration, there is a huge difference in the KD value from 3 to 4 and 5. So even different bentonite clays with the very relative content of montmorillonite, they can have different properties. They will have swelling ability and so on, but they can differ in sorption and diffusion. So, and of course, we perform all our experiments to further perform modeling, to predict the sorption capacity of the buffer material and diffusion capacity, and we should when we create the repository, it is necessary to demonstrate everybody that our system is very safe and it has a good ability to sorb, to swell, not to diffuse, and so on. So it is very important step. So it is everything that I wanted to show you today. Yes, so thank you for attention. If you have questions, I think we should discuss them outside because it's our time. Time is up. Thank you.
Так, слышно меня? Теперь я вас не слышу. Алло. Слышно меня? Эй. Теперь я вас не слышу. Эй. Скажите что-нибудь.
Камеру? Да.
О, звук пошел от вас. От
Раз,
меня.
раз. Раз, два, три. Раз, два, три. По крайней мере, микшер видит. Микшер видит.
Слышу.
О, теперь слышно.
Слышит, да?
Да, слышит.
Раз, два, три. Раз, два, три. Так, у нас идет. Раз, два, три. А, у нас
Могу
камера
повторить.
идет, да? Так.
Раз, два, три.
Линейный вход, да. Попробуем сейчас.
Люди.
Раз. Так, с камеры нет. Раз, два.
Очень громко.
Значит.
Так.
Володя, поговори.
Говорю. Раз, два, три. Слышно, нет?
Сейчас с этим микрофоном, может быть, или не имеет, что-то очень другое.
У меня все работает.
Раз, два.
Раз, два. Три, четыре. Три, четыре.
Раз, два, три.
Ой, слышу вас.
Все, так, а выход у нас должен быть... Выход должен быть... Так,
Говори. Москва.
Говорю. Раз, два, три, четыре. Три, четыре.
ну, вот так.
Володя.
Да, тут я. Тут.
Я им тесты дам подписать.
Ага.
Лучше бы что-то ты был.
Раз, два, три. Так, идем, да?
Так. Раз, два, три.
Да, про презентацию скажу.
Раз, два, три.
Но сейчас давай все-таки поборемся, вдруг получится.
Боремся вовсю. Говорю. Я говорю. Все время говорю. Говорю. Раз, два, три, четыре. Три, четыре.
Если
Раз,
мы вот
два.
что сделаем. Так,
Сделайте.
сюда,
Попробуйте.
сюда.
Если что, презентация у вас. У вас.
Раз, два.
Раз, два.
Так, у нас вообще звук с
раз,
компьютера
два.
идет?
Да,
Ручку проверю. Вот, звук неправильно сейчас.
идет звук с компьютера.
Ага, ясно. Можно сейчас интернет проверить. Включим.
Трансляцию можем пока отключить. На всякий случай. Что-нибудь слышно? Ну и чё? Хе-хей. Видно, слышно меня. Ничего не слышно. Слышно, нет? Слышно ли меня? Слышно ли меня? Слышно ли меня? Так, так. Ай-яй, громко очень.
Нет, звук пошел.
Звук
Раз, два,
идет.
три.
Раз, два.
Володя, скажи
Да,
что-нибудь.
говорю, все время говорю. Все время говорю.
А он
Не
Hide
молчу.
differential audio device.
автоматически ставится.
Вы
Да,
меня
я
просто не
должен.
слышите.
Володя,
Не хотите меня слушать?
Sorry.
Очень громко. Я вот слышу ваши звуки.
Микрофон.
Так.
Меня не слышно.
Посмотрим, что они здесь.
Раз, два, раз, два, раз, два. Раз, два, раз, два, раз, два.
Тебе здесь как в зуме нету проверить. Да, ну вот.
Есть.
Вот. Так, раз, два, три. Динамики.
Раз. Динамики работают у вас.
О,
Отлично,
вау, мы тебя
всё.
слышим.
Ага.
Огонь.
О, отлично.
Все.
Так, погромче делаю тогда, да?
Да.
Слышно? Раз, два, три, четыре.
Да. Может,
Шикарно.
Раз, два. Раз, два, три, четыре.
темный экранчик, но мы тебя слышим.
Отлично. А вот и я.
Сейчас.
Так, раз, два, нас слышно?
Очень слышно, хорошо. Звук, конечно.
Потише?
Да, очень как-то зашкаливает.
Понял, сейчас микрофон только погромче. Потому что у нас, наверное, разделение экрана. Так, мы должны и тут, и там показывать это тоже. Все. Значит, нам нужно что делать.
Ну, как у нас? Все слышно?
Да, я думаю, даже все видно. И вас видно тоже.
Отлично.
Звук тогда чуть-чуть потише сделаю.
Угу.
Микрофона. Так, вот так лучше?
Так, лучше, но тише. Так, это другой микрофон, видимо.
Ну, это с петлички.
Да, он прям
Микрофончик.
хорошо звучит,
Да?
громко достаточно, да.
Все, супер. Я тогда его кладу пока.
Угу.
Так, он вообще понадобится сейчас?
Понадобится микрофон большой, чтобы задавать вопросы из зала.
Все, окей, сейчас настроим тогда тоже. Ага.
Ага. Если они будут. Я, конечно, вряд ли смогу ответить. Так. Ну что?
Раз, два, три.
Ой, очень плохой звук. Еще раз.
Плохой, да? Понял?
Ну, в принципе, слышно. Вот
Ну,
такой.
я его сейчас чуть повыше поставлю. Ну, петличка, она отличается немножко,
Не,
поэтому...
сейчас нормально идет.
Вот так вообще. Хорошо?
Ну, пойдет. Пойдет.
Принято. Ага, окей, работаем тогда.
Угу. So, hello everyone. I'm not in Moscow anymore. For this period of time, I'm on my vacation, and yeah, it's something like 1,800 kilometers away from Moscow, on the seacoast of the Black Sea. I hope that you enjoyed your trip to Troitsk-Sergiev Lavra and enjoyed an example of Russian culture and religion of this Orthodox religion. And today I will talk with you about the project management and financial aspects of radioactive waste management, but with example of decommissioning. So it's more complex projects on decommissioning than just on radioactive waste management, because radioactive waste, they're a part of the decommissioning. So I will start to share the screen. Moment. Um, yeah. Okay. Yeah. Okay. And I don't have a very good internet connection, so I will turn off my camera just to avoid the internet failure. Okay. So we'll start with this project management and financial aspects of the so-called final stage of the life cycle of any nuclear facilities, and it will be only basics. Actually, it was planned that this lecture will be given from the specialists from our company of Rosatom, but he was not available today, so I will do this job for him. So sorry if something will be not very clear. I will try to explain how I understand these aspects, but maybe if you will have any questions, some certain questions, we will then direct them to this specialist. So decommissioning or final stage of the life cycle of a nuclear facility is quite a problematic sphere or area of the in nuclear industry, because only 35% of all projects are successful, and only 65% of all these projects, so 65% do not meet the primary criteria that was accepted in the initial state of the project implementation. So the average budget deviation for decommission project was 18% higher than it was planned in initial step, and also it was postponing, so it was lag in time, so around 11% in average for all these projects. And the decommissioning is not the only sphere in our life that fail in this project management, because these errors in planning and implementation of projects often lead to various successes or underestimation of this budgetary this financial cost and time prediction. For example, also the Suez Canal, the over cost was around 1,900% of the initial estimations, and Sydney Opera House, it was 1,400%, and Panama Canal was 200% more expensive than it was expected in the initial stage. So the failure to achieve the planned results often occurred due to insufficient estimate of the required resources, a lack of well-developed system of interaction with contractors, with suppliers, and other participants in this project, and also an absence of or just a formal approach to project management. So that means that we have a list of these procedures, but we follow them just for how to say it, just to say that we are following this list, but don't understand actually what we are going to do. And to operate, to implement the project sufficiently, we need precisely determine the cost of work. We have to prepare the supply chain, to search for suppliers, evaluate the so that they can confirm that they will get all the suppliers at time and etc. We need to select and justify the technologies that we will use, and also, of course, there is a need for a modern project management system. And there are several general guidelines, some standards already issued in nuclear industry, and there is just an example of all these books. Decommissioning strategy is dependent on the country and on operating organization of nuclear facility, and decommissioning is started not from the shutdown of the nuclear facility, but decommissioning started a long way before the shutdown. So it's a preparation of the facility for further decommissioning, and there is a step for if it is NPP, nuclear power plant, then spent nuclear fuel removal, and then all these steps they're dependent on the final stage that we or the country or operating organization is choose for this facility. It can be delayed dismantling. That means that we store or conserve this facility for quite a long time. It can be decades or even more than 100 year, and only after this it can be dismantled or liquidated. It can be the second option, immediate dismantling. That means that we liquidate this facility in quite a short period of time, in 10-15 years. In some countries like Germany or Sweden, it can be even 6 or 7 years. And the third option that is more or less accepted in Russia, it's disposal in place. That means that we prepare the facility for final disposal in the same place where it is located. We dispose this facility, put in all these engineered barriers that will prevent the migration of radionuclide that Anna already told you about. And then there is a controlled operation of the repository. It is important to understand that around 90% of all activity in the case of nuclear power plants is concentrated in reactor zone. So that means that during the preparation for further dismantling or further liquidation, during the conservation period of time, the dismantling of surrounding facilities can be done, and it will decrease the area or the territory that should be controlled. And this is important because during the conservation, the main part of all the expenses they came from this maintaining the life systems for the facility, all these radiation barriers, all this system for control, the closed area, etc. So it's very costly to maintain all this system. And in some cases, this immediate dismantling, what is the main difference in technology when we use delayed dismantling and immediate dismantling? So after the conservation, after the storage of this facility for decades or 100 years, let's say, all these short-lived radionuclides, they will disappear. That means that we can work more safe with all these equipments. We can use what to say, living or just people who are working in these areas without a very difficult radiation safety systems, etc. But during immediate dismantling, as far as the period of time is very short, the radiation doses in these facilities will be very high. That means that we have to use like robotic systems and other system that will allow us to work with such a high activities. So these two different conditions to work, high doses in the case of immediate dismantling and low doses in the case of delayed dismantling. But as far as delayed dismantling will take of decades of the storage, that means that we will spend a lot, enormous amount of money to save, to keep it safe and controlled. So when we compare the costs for delayed dismantling and immediate dismantling, it seems that immediate dismantling has benefits from economical point of view. There is a chart of this time zone of the decommission of nuclear facilities. This is again the initial step, the preparatory work. So we're preparing the facility for decommissioning. And then there is a very long period of time for decommissioning. And there is a period of time between the decommission and the final liquidation. And there is such a called zone of uncertainty, where we can either reduce the cost of the whole project or we can increase it. And so it's a very important step to evaluate our technologies, our chain of suppliers, and other factors that will affect on the cost of this of the whole project. There is just a structure of some evaluation of decommissioning of nuclear power plants. It's for different type of reactors, PVR or BVR. And you can see that this 26% and 33% they're going to a controlled access area. So it's quite a large part for maintaining all these systems, safety systems, control systems, and yeah, that's why the immediate dismantling can benefit against the delayed dismantling. And again, there's just an example of evaluation of costs of the decommission of nuclear power plant in European Union. You can see that there's a very small part that are going to project management, and for European countries, it's around, I don't know, 1-2%, and for US states, the ratio of or fraction of project of money that goes to project management, it's varies from, let's say, 5 to 7%. And there is again two approaches to manage the projects for decommission, depending on the number of power units that organization is operating. And if there are only few units, let's say 4 or less units, then it can be more effective to use to select the external project management organization, the external organization who will manage the whole project of this process. Or if the organization operates more than 5 units, like E.ON, EDF, or Rosatom, then it can be more reliable, more suitable to develop as self or the own project management division or office or whatever in the structure of the organization with the key competencies, with engineering competencies, project management competencies, etc. In Rosatom, there is different approaches for project management depending on the area of the expertise for these projects. There is investment and construction projects. There are PSR project. PSR is a production system of Rosatom. That its main goal is optimizing a process, solving a problem in the process using digital tools. Or it's projects with transactions with a shared capital. It can be research and development projects, organizational management projects, or IT projects. So all these projects, they have a bit different approaches. And all these approaches are formalized in the relevant standards. And Rosatom develop separate guidelines, separate recommendations that can be implemented in the project management system. Also, there are different levels of these documents from international standards than the national standards. In Russian Federation, it's called GOST, so it means state standard of Russian Federation. Then there are guidelines, and then corporate level recommendations for the structure of the project management, etc. And it is one of the main procedure to manage a project is the construction of the so-called Gantt charts or Gantt diagrams. Most probably you've heard about them or even used them. So Henry Lawrence Gantt was initially an American mechanical engineer and manager. And his contribution to manufacturing and engineering was recognized by American Society of Mechanical Engineers, and this society established in 1929 a special medal in honor of Henry Gantt, and this medal is awarded annually for achievements in management and service to society. Gantt himself used in actually a wide range of charts and diagrams. And this most famous diagram chart was introduced by him, not by him, but the name Gantt diagram or Gantt chart was introduced in the book of Wells Clark, where he describes the use of these Gantt charts for measurement of the performance of various systems, machines, and mechanisms. Gantt himself developed his charts firstly in the article called Graphic Diary Production Balance that was published in 1903. And later he combined his articles in his first book, Wages and Profit, that was published in 1916. So it's more than 100 years ago. And Wells Clark, he worked with Gantt, and he can be credited for retaining much of the Gantt's legacy that we have today. The Gantt chart used by Gantt and later detailed by Clark shows that each item of the that should be manufactured or should be used in the project, and also the quantity of these items they can be allocated in one line. So it's a very convenient way to show how their process will be organized and with time and all the with quantities that are required for the project implementations. A project is in general is a set of related activities, and the project these activities they are designed to achieve certain goals. And these goals they have some certain requirements for the quality of the results, for the time, and for the budget. The project management as an independent discipline started to be developed in early 30s of the last century, when such a huge company, US company like US Air Corporation, and now well-known company Exxon, it's an oil and gas company, they started to work on a large engineering projects in the United States. And later, in 1937, the American scientist Gulick performed the first development on a matrix organization for the management and implementation of complex projects. So for the first time, this practical application was in 1953, 1954 in the office of joint project of this US Air Force. And then later it was applied in the United States Navy Special Projects Office. So these were the first and most organized mechanism for achieving integration in the management of complex and large projects. As a consequences of this integration, a certain project management practice has been developed, and now it was divided by the whole project management was divided by definition of the required results, careful preparation or pre-planning to avoid future changes in plan, and then appointment of a main contractors responsible for the development and project implementations. In 1956, DuPont, this company formed a group to develop of methods and tools for project management. And later, they joined, it was all these efforts were joined by UNIVAC Research Center. And at the end, they created or developed the critical path method that is called CPM, and they developed special software that was implemented with UNIVAC computer. This CPM, the critical path method, was successfully tested in the development of a plan for the construction of a chemical fiber plant in Kentucky. Then this CPM method was used again by US Navy, and then this special PERT system was developed during the development of this initial system. So later, in 70s, in 60s, the development of project management concentrated almost on methods like CPM. And the scope of application of this network methods was expanding, and it results in many other methods like RAMPS, RPSM, and other. That is important that as far as the computing resources were development, the project management systems, they also used all these benefits of the computer system, of networking, to create new project management systems. So there is a short overview with time schedule, time frame of the project management development. What is again important here? It is a development of the project management together with development of technologies, and yeah, it's like in many other applications. There are different standards nowadays in different countries, and yeah, these project management approaches or strategies, they are fixed in different standards of international and national organizations. By 1970s, professionals from the developed countries of various continents, they formed these national and international associations. In Europe, it is International Project Management Association, IPMA. In North America, it's Project Management Institute, PMI. In Australia, it's Australian Institute for Project Management, AIPM. And in Asia, it's Japanese Engineering Development Association, in AA. And then over time, this organization established very close mutual contacts to exchange information, ideas, and now a kind of project management world was formed, and this project management world brought together specialists from different continents, countries, organizations, field of expertise, cultures, and everything. And all this played a significant role in the development of the project managements. Now we have two basic approaches for the project management. It's a process approach and a competence approach. And so the process model, it is based on the process management model and takes into account the main phases of the life cycle of the project. So to obtain a result that is required, it is enough to build a process, a quality process. And this PMI organization and Prince2 organization, they use this process model. The competence model is a bit different. It is based on the idea that it is important to involve the key specialist in a project that have the relevant competences for the certain step in the project. So the focus in this model is on the competences of the project manager. And yeah, process approach that is implemented, for example, by PMI. It's so this PMI has so-called PMBOK. It's a project management body of knowledge, and it is the sum of professional project management knowledges. There are different generations of this book. First, it was released in 1996. Yeah, it was the first edition of PM book, and then every 4 years it was updated. So the last one was the sixth edition was released in not in 4 years, but in 5 years after the fifth edition, so in 2017. And the next one is planned to be released in 2023. The most popular countries that used the PMI approach is the USA, Canada, Mexico, some Asian countries, including China and India, and the 70% of PMI members are located in North America. All projects activities are divided into 49 processes according to this process approach to the project management, and there are 5 process groups. All these 49 processes, they are grouped by process groups and areas of knowledge. There are 5 main process groups. So initiating process group. That means the processes that are required to start a new project or a new phase of project. That means that in general, it is assumed that the project is formally approved already and assigned to the project manager. And this group includes 2 main processes. Development of the chart of the project is maybe Gantt charts, for example, and the definition of the project participants. The next group is the planning group. It means the process that are related to defining and planning the scope of the project, as well as planning how to implement it. It is the largest of the 5 groups with 24 processes. And this group designed for detailed planning of all work on a project. Volume of the work, schedule, budget, stakeholders, and the main results of this stage is the project management plan. The next group is the executing process group. That means that processes that are directly related to the implementation of activities or the project tasks. And this group is the most of the project activities take place. At this stage, most of the budget is spent and future project deliverables are generated. This group includes 10% of the project management processes, but again, most of the budget. The main focus of activities, the main focus of this group of processes are on activities and tasks that are aimed at assuring the non-interruption of the work, establishing interaction between different participants, response to risks that can arise, etc. The control process group is the second largest group that includes 12 processes that are related to tracking, monitoring, reporting, and controlling the progress of the project. And the final process group is the closing process group. That consists of just one main process, the project completion or completion of one of its phases. In this process, it is important that the client accepts all the results of the final stage or entire project. In addition, it is necessary to complete all documentation and provide its storage, as well as eliminate flaws in the project or its phase. The competence approach that is implemented by IPMA, that is the first and the largest international organization in the field of project management. So it was established in 1965, united 73 countries, and this organization provide development and promotion of professional project management in all areas, not only in decommission, but in any areas of expertise. This organization also includes almost all developed European countries, as well as Turkey and Egypt. Yeah, in Russia, the organization called SoftNet that was founded in 1990 is an organization that also used this IPMA approach. The main professional competences can be divided on 3 areas of competence that are divided by areas related to people, to practice, and to context. And there are these competences that you can read later. We will go now to the next part as financial aspects. It's very quick. I hope that, so we have now something like 5 minutes left. I will try to be fast. So financial issues is the key issues in any project management, and the goals. It's improve the quality of cost evaluation during the financial planning, and also the formation of adequate mechanism of accumulation and consumption of all these financial reserves. And there are again several guidelines and standards that are released to help you to understand the main routes for financial planning. And when we talk about the decommissioning of the facilities, the stages of the cost evaluation, they take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps, going from the assumptions of costs, like determination of the main financial economic indicators. Then there is determination of stages, duration, technologies that we will use for decommissioning or for radioactive waste management, etc., etc. And assumptions, what are the assumptions? They related to the final result that we would like to reach. It is approach to radioactive waste management, also including very low level waste. It is also approaches that we will take to account for spent nuclear fuel management at the site, and it is approaches to separate the responsibilities between the state and the operating organization. That is a very important step. And the same examples of assumptions that are used for evaluation of decommissioning costs against different assumptions for dealing with nuclear power plants, research reactors, or other facilities. And again, there are several documents. The first one was this yellow book. Now it is outdated, and as far as huge experience was already accumulated by international organization, international experts. Now there is this international structure for decommissioning cost of nuclear installations that has guides for evaluating the cost of different activities, and this blah, blah, structure of costing is presented in the form of hierarchical structure, where the work of the third level, so it's very detailed works, for example, how we will remove precipitates from the pipelines. It's just an example. All this detailed single works, they are grouped, and this group then again grouped together as a group of single works of the second level, and then they are grouped in the main types of work, so it is types of the first level in this hierarchical structure. And each kind of works, the cost of these works can be divided by 4 cost groups, like labor cost, capital investments, other expenses, and some unexpected expenses. And there are several. There is this document, Cost of Decommissioning of Nuclear Power Plant, released by NEA, and it is a unified methodology that allows to estimate the cost for different NPPs in different countries. So in this document, the comparative analysis has been already done for various characteristics of nuclear power plants, for different strategies that are implemented in different countries. So it's very detailed analysis that can be used by anyone. And the cost approaches from the point of the accuracy of the result of this approaches can be divided into 3 main ways. So it's order of magnitude estimation, budgetary estimation, and definitive estimation. So they have different detalization level, and as far as they have different detalization levels, the uncertainty or accuracy is improving from step to step, and it started from, let's say, 50% accuracy of estimation of cost, then going to, let's say, 5 to 15%. But anyway, from these numbers, you can see that even in the best case of this definitive estimation, the level of accuracy is only 5 to 15%. So it's a rather high deviation. And there is 5 cost estimation methods, like bottom-up technique, specific analogy technique, and parametric technique, and cost review update technique, and finally the expert opinion technique. So the bottom-up technique, it is calculations that are based on the data of the whole technological map or schedules, taking account the working hours, the technology that we will use, and based on these documents and prices, we can make calculations about the direct labor cost, about equipment costs, and other costs. Specific analogy technique, it's a rather simple technique. It is based on the use of the cost of the similar projects, and you just adjust or feed the parameters in these similar projects, taking account the differences in that previous project and in your actual product, difference in level complexity and technical operational characteristics, etc. Then there is a parametric technique that takes data from the databases, again for similar systems or subsystems. That means that you can use the statistical analysis. That means that to use these parametric techniques, you had to have a lot of different projects that are implemented already before. And the cost review estimate also the cost for similar projects with all the updates in techniques. For example, it is similar projects of radioactive waste treatment, but the technology is developed nowadays and the cost of them decreased, etc. So you review and update all the cost for the technique that are used nowadays and update this information for similar projects from the past. And now you have cost evaluation for your new project. And then if there is no sufficient data that can be used in all these methods, then you can use this expert's opinion. And to do this, you can invite several experts, as many as you can invite, as many as you know, and they will try to estimate the cost as best as they can. So this is all for this lecture. This lecture again will be, you can find it in the folder. I think not now because I just sent it today morning to Andrei. And so now you will have a lunch break. After that, you will have an evaluation of your practical tasks, and also you will have some final tests. And again, it is not for any estimation of your level. It's just to see if this school was as useful as we expected. Also, it will be some feedback list, a list that you will fill in, and yeah, we will see. I hope personally that everything was fine and you are happy with this school. This is all from my side for today, and I wish you. I don't think that I will see you later, and I wish you a safe trip back to your home, and yeah, hope to see you again someday. Okay,
Thank you very much, Vladimir.
bye.
Раз, как слышно меня? Коллеги, вы меня слышите? Мы вас не слышим.
Да, Сергей. А меня слышно? Потому что мы вас тоже не слышим. Да, да, хорошо. Ага.
Раз.
Да, добрый день. Так.
Так, у вас звук пока выключен. Вы меня слышите? Отлично.
Осталось вам звук включить.
Алло. Алло.
Да, слышно. Нам слышно. Все, отлично.
Guys,
Да.
currently we have a technical tour. Yeah, in our partners, so it's online.
Great.
But
Да, давайте все, тогда начинаем.
Okay, dear colleagues, dear ladies and gentlemen, let me introduce myself. I'm a chief commercial officer of NTP Radica, and now I will show you our production branch in Obninsk. So now we at the production department, and I will try. Let me little bit check the picture. This is our production area, and now we will demonstrate some approach which we apply for production equipment, and also we will show some samples of our products which are available in our production at the moment. And let me say a few words about our company. Radica, NTP Radica works on the market of nuclear industry more than 30 years. And now we have a staff about 160 persons totally in the group of company. Now we have offices in Estonia, in Latvia, in France, and 3 offices in Russia. In Moscow is a former branch of Canberra. In Obninsk is the main production department and main engineering department. And in Volgodonsk region, it is our service department for nuclear power plants. Here you can see our production area. I can say that is more assembling area, because all production operation we complete outside, and here we perform just assembly. And if you look from the top, you can see the big glass windows. It is the office area where some of our engineering works, and they support assembling parts. It is a reason for we are located very close to assembling area. What else? I can say that since 2008, Radica is an exclusive industrial partner of Miriam Technologies Group, and we not only produce our own equipment, we also localize some products of Miriam Technologies. For example, like these units, and we produce this equipment under a special license agreement with Miriam Technologies. Okay, in our production, we implement, of course, quality management system, and the production processes are the part of this quality management system to provide our clients the good quality of products and services according to not only Russian standards, also as well as international standards. And I think you can get acquainted with our production processes, and Alexander Nikulkin, who is the head of production division, will support us and will demonstrate some key steps of production. I will translate. He will speak in Russian, sorry, but I will translate what he said.
Итак, наше производственное помещение, оно начинается у нас вот здесь, идет оно вот в таком направлении, начинается с инженерного отдела.
Okay, our production area start from this point and moves to this direction, and we start from the engineering department.
Здесь у нас хранится вся необходимая техническая документация, необходимая для сборки оборудования.
Here we locate the stand where we put all necessary documentation, technical documentation, according to production orders, which are complying at the moment on our production.
Технологический процесс сборки начинается у нас от самого участка.
Okay, the technological process of assembling started from the can I say area of completion of components for assembly.
Здесь у нас находится участок комплектации, то есть все комплектующие, которые нам необходимы для изготовления оборудования, приезжают к нам сюда и выдаются под каждый заказ отдельно.
Okay, for each production order, we combine here, collect here all necessary components, and each sort of components are put it on this stand according to production order.
Изготовление начинается, когда у нас есть вся техническая документация, все комплектующие по данному заказу для данного оборудования находятся здесь.
So we are starting production when we had all necessary or required technical documentation, and all components are located in our small warehouse.
Когда комплектующие пришли, здесь происходит их проверка и сверка, чтобы количество и наименования совпадали.
Okay, here we also perform the incoming quality control of components, check the marks, check some characteristics.
Вот в таких синих ящиках хранится у нас вся документация до момента сборки.
Okay, this blue box applies for temporary storage of components.
При старте изготовления все комплектующие в этих ящиках переносятся в зону сборки.
Yeah, so all box are marked. And after starting the production, these components are transferred to area of assembly.
Зона сборки делится на два типа. Это мелкогабаритная сборка и крупногабаритная сборка.
Okay, we can divide assembling area into two parts. The small sized item assembling and like what is like like this, and the oversized items assembling like these hoods, these cabinets.
Если у нас мелкогабаритные изделия, то у нас собирается здесь, это рабочее место, и за каждым рабочим местом закреплен свой инженер по сборке.
Okay, here the working place of assembling engineer who performed some operation with small items, and each working place. Okay, so assembly engineer has his own working place, and he has also own tools, all equipment for assembly.
Соответственно, комплектующие по одному заказу за пределы этой зоны не выходят.
Okay. At one moment, here we collect the all necessary components, all required tools and documentation only for one production order, to exclude any mistakes.
То же самое здесь с крупногабаритной сборкой. Есть базы, где хранятся комплектующие, есть, соответственно, стойки, где хранятся.
For oversized item assembling, we also have a separate area for each production order. We have a stand with technical documentation, which applied only for this production order. We also have a stand with components. So this division allows us to exclude mistakes during the assembly.
После сборки оборудования и контроля всех операций мы переходим к приемо-сдаточным испытаниям.
Okay, after assembling and performing on checking operation, we are coming to area of factory acceptance tests.
Здесь же проходит наладка оборудования.
Here we perform some kinds of supervision operation.
После приемо-сдаточных испытаний и наладки мы передаем оборудование средству измерения в поверхность.
Okay. After final testing, if everything is okay, we are transferred equipment to meteorological testing. It is a special requirements for Russian regulators. In Russia, it's called the meteorological verification. In international production areas, it is like a calibration of measuring devices.
После завершения основных технологических операций оборудование упаковывается на участок упаковки.
Okay, after all technological operation, assembly operation are completed, we are going to parking area. This is there is some marks on the floor. Also, we divide the area by tables. And here you can see the completed products and materials for packaging.
Если оборудование упаковано, то проводится контроль, финальный контроль, и оборудование переходит в зону отгрузки.
Yeah, I can add that each packing materials also marked for each production order, and after products which are also checked. We completed the final check. Okay, we are checking that all documentation which is required for this kind of products also put into the box. We check the quality of wooden box. We check the packaging inside of this box, and after everything is complete, we move the products to shipment area.
Из зоны отгрузки упакованное оборудование попадает на склад готовой продукции.
The shipment from the shipment area, the products transferred to the warehouse, where all items are waiting while the customer will pick up it.
Также есть у нас участок опытно-конструкторских работ.
Давай сначала про ремонт, может, скажем. Okay.
Также к нам поступает в ремонт наш отдел сервиса оборудования с различных станций и из тех мест, куда мы их поставляем. И здесь ремонтируем генеральный.
Also, we received some requests for repairment of our equipment, and we also has an area for repair. You can see here the whole body contamination monitors. Oh, I can say that it is a Medium Technologies product, and let me introduce that from this year, Radica received the authorization from Medium Technologies, and now Radica is official authorized service center of Medium Technologies in Russia and in countries of from former Soviet Union. Okay, after repair, when repair is completed, the product also transferred to the packing area, packed and shipped to the customer. Okay. Now we will show you the area of research and development. Our engineers design new products. Okay, here some sampling stands for iodine monitor. Here you can see prototype components for monitor for environmental measuring. It is a new product. Now it's only the beginning of design.
После заключения отделом работы, если вся техническая документация правильно, все было собрано, мы уже не можем делать установку производства.
Okay. After R&D part is completed, all documentation transferred to our engineering department and our production department to how to say in English, sorry. It is a special operation for starting the production. When we revise all documentation, that everything is right, and after completing some tests, we can be sure that we will be able to provide the quality production with high quality.
В принципе, все, мы прошлись по всем зонам, по всем участкам, и вот так вы видите.
Okay, now we are finished our introduction of our production area. So the production process is not so big, but it is has a structure and special operation which should be completed step by step. And now I let let me show you some samples of our equipment which we produced and assembled in our in this production area. I think you know that Radica specialized. The main feature of our company is equipment for spectroscopy measuring, and now you can see whole body monitor for controlling of international dose rate from the man body. You can see the chair and different types of spectrometers. One spectrometer for controlling of thyroid. One spectrometer, it is a high purity germanium detectors for checking internal radioisotopes inside of body. It is a new product. Now we are producing this product under third safety class because it's new requirement of our regulator. This kind of equipment in Russia classified as third safety class equipment. Also here you can see spectroscopy monitor for liquids. This is a measuring tank with protected by lid, so we can measure the liquids which fill inside the tank. And more complex solution is a spectroscopy high purity germanium monitors of radionuclide in liquids. You can see just here the measuring part with germanium detectors. We apply conveyor germanium detectors. Also here you can see some valves which manage all sampling lines. I will show you some stands for samplings. We can we can take the sample from up to 15 points, as I remember. It is also a product which certified under as a third safety class equipment and applied for nuclear power plants. Okay. So, and let's come back to R&D department. R&D, sorry, department area. Let me say a few words about new products, which is an environment monitoring system, which also apply spectroscopy solutions. It is the feature of this system is a spectroscopy. It is a first system in Russia which can identify the radionuclides in area, in air or outside of this system. So before this moment, we had requirements only to measure dose rate without identification of radionuclides. Now we try to solve this problem. As you can see, we apply different spectrometers technologies to solve different tasks from the technological control, technological radionuclide monitoring, up to individual dosimetry systems. Okay, so I've completed my story, so you can ask the questions.
Sergey, thank you very much. Do you have questions for the Sergey?
I have one.
Yeah. Yeah, please here.
Please show the instrument and explain little bit the science behind the spectrometer. What you use to determine the radionuclides in the air? Gas spectrometry.
Okay.
Please show the instrument and the science behind it. How you detect the radionuclides in the air?
You means environmental monitoring system, yes? Correct?
Yes.
Okay. We are going to apply scintillator spectrometers, which based on lanthanum bromide free to receive the better resolution for identification of radionuclides and to be more flexible in the different temperatures range, because you know that sodium iodine detectors can accurate work up to plus 50, plus 55 degrees of Celsius, not more. Due to so for it was a reason for we decided to apply lanthanum bromide crystals. I cannot explain some details because it is we are just start this development. I think we will introduce some results during next meeting, maybe.
Okay. What are the radionuclides you are capable now to detect?
Sorry, could you repeat, please?
What are the radionuclides you are capable to detect in the air, in the atmosphere right now?
Yes, you're right. Yes. Sorry. Right. What right now?
What are the radionuclides specifically you are able to detect with present instrument?
Sergey, which one
right now
for radionuclide? Which one?
Okay. Different radionuclide. As I remember, lanthanum bromide has a resolution around 4%. It led us to receive the measurement of some natural радиоизотопс.
Сергей, там вопрос был, какие радионуклиды он позволяет детектировать в воздухе?
Okay, я понял, что, okay, I cannot give you the concrete list of radionuclides. The feature of lanthanum bromide is a very nice resolution of spectrometers which we received. It depends. It let us to divide the high ratio of isotopes, right, of radionuclide, which is not possible to measure using sodium iodine crystals, for example. If we will talk about this system, let me show you. Come back to this system. This is a spectroscopy gas monitor, which we apply for checking ventilation stack in nuclear power plants. Here we apply the high purity germanium detectors with very high resolution, and in this task we are able to measure more than 50 radionuclides. More than 50 radionuclides at the same time.
Great.
But of course, it is a more complex system. They are really very expensive. They are required the special conditions because it is like placed inside of a building. And if we talk about area environmental monitoring, of course, we have another condition for measuring, and we have to take it into account during the design.
So the other spectrometer was?
Yes, of course, and for spectrometers also. Because you can see here the
This is from Russia. Where from the previous spectrometer?
okay.
This is from Russia. This is from Russia, right? But yeah, which country this is from?
If you talk about only spectrometer parts, we apply the Canberra spectrometers. This is Canberra now is a part of Medium Technologies Group, and we apply their products because we are partners. But if we talk about the system, it's the system designed by Radica, and all algorithms, all measuring algorithms designed and programmed by Radica.
Сергей, а для какой это страны сделано? Это для России или
Вот
для...
это такой. Yes, this is equipment for Kursk NPP. It's for Russian for Kursk NPP. This is for new power units, which is now under construction. Also, we already installed the same system in Smolensk NPP, in new power units in Leningradsk NPP. We assigned contract for PAKSH in Hungary, and now we won the tender for Rupur in Bangladesh. So I think it's a really very nice product. Now we are playing tender for Chinese Suidapu and Taiwan new power units which are under construction now. So we have a very big reference for nuclear power plants at the moment.
Very much.
Any questions? No? Okay.
Thank you. Спасибо, Сергей. Thank you very much.
Okay, thank you very much. I suppose that next time we will show you in our products. For example, now we are starting the project for waste management system, where we also apply the spectroscopic solutions. Unfortunately, we could not show it now, but next time, welcome.
Thank you. Bye-bye.
Okay, bye-bye.
Пока, спасибо.
Hi guys. Thank you very much to come to us. So from me, very much. I will be glad. Was glad to see all of you. And once again, of course, if you will back in November, it will be perfect for me. So I want to introduce our dean, Stepan Kalmykov. Stepan.
Yes,
Are you
I'm
here?
here.
Oh yeah. Okay.
Can you hear me?
Yeah. Perfect.
Okay. So it's my great pleasure to say a few words to you as participants of our International Summer School on Radiochemistry. So the main thing that besides I am the Dean of the Chemistry Department, that is really a large facility, I am a nuclear chemist by the trainee. So I still remember many things in radiochemistry, in nuclear science. And so I would like to, first of all, thank you for coming. Thank you for coming to Moscow, come and to attend our meeting offline. So this is very important that we can communicate, you can communicate face-to-face with lecturers and between yourself. So this is very important to have this personal relations. They are always constructed during different conferences, workshops, seminars, and this is very important. I would like to say that I think that our meeting was quite successful despite all these difficulties related to the COVID restrictions and limitations, and despite the very hot weather in Moscow. So we just few words of statistics. We had both online and offline participants, and speaking about offline participants, we had 29 attendees from 12 countries, and I would like to mention them. This is Turkey, Belarus, Kazakhstan, Ethiopia, Serbia, India, Egypt, Uzbekistan, Slovakia, Cuba, Nigeria, and Bolivia. And we also had 20 participants from 10 countries that were online, so they were not able to come, and I hope that they will come to the next meeting in November. So this is Bolivia, Iraq, Zambia, Saudi Arabia, Czech Republic, Nigeria, Germany, Turkey, Uzbekistan, and Egypt. So we have a large family of members, of attendees, and I really hope that you can come and attend. You'll face another Moscow in terms of the weather. It should be quite cold at that time, and I hope that in November there would be much less restrictions and limitations in terms of the international travel and going to some technical visits, etc., etc. So I think to finish with my remarks, I would like to mention the very important thing that we are entering the new reality where decarbonization scenario is actual, and one of the main aims of the decarbonization scenario is to decrease the emission of carbon dioxide, and the energy production is one of the main sources of carbon dioxide, and nuclear chemistry and nuclear energy certainly one of the ways to effectively face this decarbonization scenario. So, but as you know better than I do, that the problems of the nuclear energy is the problem of the nuclear waste generation. So the topic of the nuclear waste is extremely important. This is an international issue. This is not only the problems, technical and scientific problems that countries with large number of nuclear reactors are facing, but a lot of different countries facing with nuclear waste problem. And that's why the topic on the nuclear waste management, characterization, disposal, and many things are really very important in terms of the international collaboration, and they attract a lot of scientists, a lot of people from many countries. So I think that in your hands there's the future of the nuclear energy, and definitely you would find the solution to minimize the volume of the nuclear waste that are generated at different stages of the nuclear waste cycle, and this is the salvation of both environmental and economical problems. So I wish you all the best. I wish you to overcome all these difficulties related to COVID infection. I certainly wish you success in your work related to nuclear sphere, related to radiochemistry, and I really hope that I really hope to see you next time in Moscow in November. So thank you very much.
Thank you very much. So guys, now we're preparing some diplomas for you. I want to ask Olga to help me, please.
Yes, we will do it like that, if you don't mind. So I will name the person and we invite him.
Okay.
Him or her kindly to come here for your diploma, okay? So let's start. Khaled Reda Abdelhamed El-Shahat.
Okay. Okay. From here. Okay.
Okay.
Yeah.
Khaled, please keep your certificate.
Come here. Yeah. Thank you. Thank you very much. Thank you.
Sholpan Nazarkulova.
Yeah. Саша? Да? Давай мы их подвинем. Да? Да. Thank you. Спасибо. Спасибо, поздравляю.
Irma Kibatu Berihie.
Да. Хорошо.
Катерина Литвинская.
Пожалуйста.
Абир Махер Хасан. Mahmud Cüneyt Kahraman.
Oh, sorry.
Okay. Yeah, perfect. That's all.
Suleiman Fatih Osman.
Suleiman.
Okay.
Perfect. Once again.
Juan Francisco Valdez Rodriguez.
It's for you. Yeah, thank you.
Thank you.
Benigno Mamani Cuenca.
Very good. Yeah, thank you.
Mega Venugopal.
Thank you.
Ayşe Nur Arafçı.
Congratulations. Perfect.
Ahmed Hari Alisakov.
Yeah, good.
Thank you.
Perfect.
Abir Shihata Mahmoud Shkrofi.
Yeah. Yeah, perfect. Congratulations.
Hesham Mahmoud Hamed Mohammed.
Congratulations. Once more.
Mohammed Omar Hegazi Al Sayed.
Oh, yeah. Congratulations.
Meryem Seferinoglu.
Congratulations. Yeah. 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 Yeah, perfect.
Aum Nirajana Mishra.
Congratulations, my friend. Yeah. Good jacket.
Thank you. Alexander Zaruba. George Petrovich.
Congratulations, George. Huh? Yeah, perfect.
Carlos Sebastian Mamani Coenza.
Congratulations, guys.
Ahmed Ismail Ali Alazaka.
Congratulations. Поздравляю.
Kamal Kayode Abul Rahim.
Congratulations.
Ines Abdal Hamid Shrout.
Congratulations. Yeah. Come in, come in. Yeah.
Mohammed Mustafa El Said Mustafa Atta.
Congratulations. Yeah, like this. Yeah. Not only white. Yeah, perfect.
Ahmed El Sayed Abel Sattar El Sayed Shaheen.
Congratulations. Yeah.
Mohammed Hanfi.
Congratulations.
Simona Sandalova.
Поздравляю. Yeah. Yeah. Another guy. Yeah. Thank you very much. We are finished. Stop. Not. Yeah, of course. Yeah, we have a, yeah. We plan to make a big picture with, yeah.
Yeah, you can do it outside, but here in the list with you both with certificates.
Yeah?
Yes, you can also do certificate. Yeah.
1, 2, 3. It's fine.
Hi. Is it okay?
It's here.
Giving your certificates. Okay.
Makes sense. Yeah.
Maybe I can ask to our team to
Connect again, huh? Hi, hi. Says, is it working? You can't hear it? It is green?
Нет, ну потом. We will go downstairs, right? We will stand on
Konuşma yapacağım ya. Kapanış konuşması söz verdim. Dün sen yoktun. Söyledim yani. Uyuyordum pardon değil mi? Uyuyordu. Benim kucağımda uyuyordu. Ah. Hi my friend. My first Russian friend.
Yes, I will send you information. First of all, we found out information about this tool. Has a and just a few hours and the link for application to everybody. But anyway, we will not miss it. Sorry. Yes, who may communicate and who respect. Yes, absolutely. Absolutely.
You have a data who will say who responded that to choose.
Степан.
А где это? Это в бункере?
It's okay? Hi. Okay, thanks everybody. I prepared a speech to express all our feelings. I wish you share it. Hello, Mr. Professor Stefan, and dear colleagues and dear professors. We have came to the end of this amazing organization. We start at the reception with the COVID test and go on with ice party, experiment, lectures, excursions, and applications. I'm currently experiencing opposite emotions at the same time. I think everybody has similar feelings with me. First of all, we feel very lucky to be able to meet you, valuable professor and experts of their fields, and happy a chance to exchange our information and ideas. On the other hand, like all of you, we feel a bit sadness of the end to reach end of such a beautiful organization. However, I believe that these strong ties established here will pave the way for new scientific collaboration in near future. This gives me a relief. Special thanks goes to participant coordinator Natalia Mateeva and Olga Yakubova, and organizers Rosatom technician Ilya Filipev and Andrei Putyatin, who took part in the realization of this summer school by struggling against extremely difficult conditions despite this COVID-19 epidemic condition. In addition, we would like to thank the Rosatom for this unique opportunity to support despite the difficult economical condition affecting the world, provided such a summer school where valuable scientists from many countries such as Uzbekistan, Egypt, Turkey, Serbia, and else. We would like to thank to all of our instructors, Vladimir, Anna, Natalia, Sergey, Mihail, and all, who conveyed their knowledge and experience to us on the subject of radioactive waste management and took part in the preparation and execution of the experiment and all applications and answered our endless questions tirelessly during this summer school. Okay, we are also grateful. We are also grateful to Andrei Putyatin again and Olga Yakubova for their great efforts to meet all our requests and demands. For example, from transfer, accommodation, shopping, classroom, air conditioning, as too much, and from arrival to Moscow till the departure. In addition to this valuable knowledge we gained during this 12th day, I wish that the friendship and unforgettable memories we establish here in social and cultural programs such as excursions will remain forever. Finally, we hope that this young, dynamic, and harmonious team will come together within the new members at another meeting as soon as possible. And I invite all you give a standing applause to everyone who contributes to this distinguished organization. Yeah, applause. Organization. Okay, thank you very much. Thank you very much. Okay.